Today we will discuss about the energy band diagram of PN junction and we will derive the ideal diode equation. So we already drawn the energy band diagram of PN junction under equilibrium case in the previous lecture, and now we will derive the energy band diagram of PN junction under equilibrium condition and biased condition. Biased condition means forward bias condition and reverse bias condition. So biasing means we are applying a DC voltage to the PN junction diode. So at equilibrium means without any external voltage. So we can draw the energy band diagram of equilibrium case, forward bias condition and reverse bias condition. And the first one, so this is P semiconductor and this is N semiconductor. So before joining, this is the condition. So this is EC and this is EV and EI will be in the middle of the band gap. So this is P-type semiconductor, so the Fermi level location will be closer to valence band. So this is EF. Similarly, for N-type semiconductor, the energy gap should be same. P and N are, you can assume it as silicon semiconductor, so the energy gap should be same, EC, EV, and EI is in the middle of the band gap. And for EC, the location of Fermi level will be closer to EC. So this is two isolated P and N junction. So under equilibrium condition, so equilibrium means the external voltage is 0. So we have studied the working of the PN junction diode formation and how barrier potential is created, that we already studied. So this is the depletion region, this is minus plus region. So this is PN junction diode without any external bias or the equilibrium condition. So we have to draw the energy band diagram of this PN junction. So first draw the EC, draw the Fermi level of P-type. So P-type I am not changing. So EC, EV. So here this is the P-type. So I am redrawing the EC, EV, EI, EF again for P-type semiconductor, and this is EF. And here the depletion region is formed due to the alignment of the two Fermi levels on P side and N side, or we can say at equilibrium the Fermi level will be constant, so we can extend this Fermi level to N side also. So actually this Fermi level is aligning with the Fermi level of P-type, or we can say the Fermi level is a constant at a equilibrium condition. So this is the Fermi level for the PN junction. If we draw the Fermi level, we can draw the N-side conduction band. The N-side conduction band will be closer to EF. So EC, this is EF. So EC we can draw closer to EF. And EV with the same band gap, with this band gap we can draw EV. EV will shift downwards. Since EC is shifting downwards, to align the Fermi level with the P region. P and N region Fermi level should be aligned to form the depletion region or the junction. So EC, this is EV and this is the N side. Now we can join this EC and this EC. So this is the conduction band energy level for the PN junction, and similarly we can draw the EV and this is EC and EV. Similarly EI here it will be in the middle. So here also we can draw the EI level. So this is the depletion region area. So this is the depletion region side. So if we look at the energy band diagram, we can see the conduction band, the intrinsic level and the valence band energy are having a slope in the depletion region. So here we can see the conduction band is rising as it go towards the P side. Similarly the valence band is also rising as it go towards the P side. And similarly EI also. So EC, EV, EI have some tilt across the electric field region or the depletion region. So electric field is existing in this region. Electric field that we already studied, the maximum value will occur at the junction, at the middle of the junction, that already we studied. So the electric field is in the direction plus to minus. So this is the direction of electric field. So we already studied in Einstein relation, in the direction of electric field the electron energy level will rise. So the direction is in the minus x direction, so the electron energy level will rise in the direction of electric field. So that's why here the conduction band is tilting, so it is rising towards the P side. Similarly EV is also rising towards the P side. So this is the reason for the tilt across the EC, EI and EV in the depletion region. So, and this bending of conduction band, this energy difference we can mark it as QV0. QV0 means the contact potential measured in electron volt. So QV0 means it is a value of contact potential. So this is the contact potential. We know that contact potential means the electrostatic potential on N side minus electrostatic potential on P side. So this is the value of V0. This is the electrostatic potential on N side and this is the electrostatic potential on P side. So this we can mark in the energy band diagram. We have to mark it in the energy band diagram. So this is the, and this energy difference is known as QV0. The value is measured in electron volts. That's why QV0. So this is the energy band diagram of PN junction under equilibrium. So the Fermi level at equilibrium condition is always a constant. So this is the band diagram for equilibrium condition. Now we can draw the band diagram for biased conditions. So biased condition means we are applying an external voltage. Here the voltage, external voltage is 0. For the bias condition we have to, so this is the PN junction, and forward biasing means the P region is connected to, this is the P region and this is the N region. The P region is connected to positive terminal of the bias and the N region is connected to negative terminal of the bias. So this is, we can mark it as VF. This is the forward bias voltage, and we have already studied this for a PN junction diode under forward bias condition. The barrier potential will decrease. Since the depletion region width is decreasing, the width of the depletion region will decrease during forward bias condition. So we can say the width during forward bias condition, depletion region width will decrease and the barrier potential or the contact potential value will also decrease. So the barrier potential or the contact potential value will also decrease. So these changes we have to draw it in the band diagram for a forward bias condition PN junction. So if we draw the PN junction diagram under forward bias condition, we know that the V0 value will decrease. So V0 decreasing means this is the band diagram. So EC, EV. So if we draw the previous diagram for equilibrium condition, here the value of V0, the value of this value is decreasing. So this energy difference is decreasing. So this is decreasing means the value of EC will move upwards. The value of Q0, the contact potential, will decrease with respect to the applied forward bias. So the QV0, this energy difference is decreasing means the value of EC will shift upwards. EC is shifting upwards means the value of EF will also shift. The EF will also shift upwards, EI will also shift, and EV will also. So the value of EC, EF, EI and EV, or we can say the whole end region diagram will shift upwards since the value of QV0 is decreasing. So we can draw the band diagram for PN junction under forward bias condition. So this is EC and this is EV, and this is the location of EF, and this is EI, so P side. The QV0 value is decreasing, so this is the value, and the Fermi level will be moving upwards. So this is EF and this is EI and this is EV. So here this is the location of Fermi level. So this is the Fermi level on N side and this is the Fermi level on P side. So here the Fermi level is not a constant, or it is not on the same level. So here EFN, it is much higher than EFP. So the reason is our contact potential, the contact potential value QV0 is decreased with respect to the applied forward bias voltage. So the value will be QV0 minus VF. This is the new value for that contact potential. So due to this decrease in barrier potential, or due to the decrease in the width of the depletion region, the band diagram will change and the Fermi level position will also change. This is the condition under forward bias condition. So this is the biasing condition, or the first one, that is the forward bias condition. So with the applied voltage, the contact potential will also decrease. So the Fermi level location will change. Similarly, if you know the forward bias condition, you can draw the reverse bias condition also. So the reverse bias condition, this is PN junction under reverse bias condition. Under reverse bias condition, the depletion region width will increase. The depletion region width will increase during reverse bias condition. So reverse bias condition means P is connected to negative and N is connected to positive. So this voltage is VR. So the applied voltage is the reverse bias voltage. So the depletion region, so now the width is, this is the width W, or here this is the width. So depletion region width will increase on reverse bias condition. So if we draw, then also the barrier potential, so here we can say the width increases and the barrier potential or the contact potential value V0 will increase. So if we look at the energy band diagram of equilibrium case, we are drawing the forward bias condition and reverse bias condition with respect to the equilibrium condition. So by considering the equilibrium condition, if you apply a reverse bias voltage, then the value of QV0 will increase. The barrier potential will increase. This value is increasing. This value increasing means EC is shifting downwards. EC shifting means EF will also shift downwards, EI will shift downwards, and EV will also shift downwards. So the full band on the N side will shift downwards as the barrier potential on the N side increases. So we can draw the the reverse bias condition, that is EC. So P we are not changing, so while drawing P should be kept constant. So this is EC EV, and this is EI, and this is EF on P side. So here the depletion region is increasing and the barrier potential is also increasing, so we can draw EC much lower. So this is the value of EC, and this is the value of EV and EI, and this is the location of Fermi level. So this is EC, and this is EV, and this is EI. So if we look at the Fermi level location, the Fermi level location on N side is below the Fermi level location of on P side. So this value apart from the equilibrium value, it is increased. So the V0 value is increased, barrier potential or the contact potential is increasing to a value V0 plus VR. So this is the reverse biased band diagram. So we have to understand the difference in the energy band diagrams of equilibrium condition with the bias condition. Under equilibrium condition, the Fermi level is a constant, and during forward bias condition and reverse bias condition, the Fermi level is not a constant. Also, the barrier potential is changing. The barrier potential is changing from QV0 minus VF for forward bias condition, and it is changing from QV0 plus VR for reverse bias condition. So these are the energy band diagrams under equilibrium condition and forward biased and reverse bias conditions. Next, we will study an important topic in solid state devices, that is the ideal diode equation. We can derive the ideal diode equation from the concept we have already studied in all the first and second modules. So we are going to derive ideal diode equations, and some approximations are used in this derivation, and we can start deriving the equation. So we have studied the expression for contact potential V0, that is V0 is equal to KT by Q. This is the equation. V0 is equal to KT by Q natural logarithm of PP by PN. This equation we have studied, and this equation again we modified to KT by Q ln NA ND by NI square. So by considering this equation, we can write QV0 by KT is equal to ln PP by PN, arranging this equation, and from that we can obtain the value of PP and PN. PP by PN, that is PP by PN is equal to e raised to QV0 by KT. So here QV0 by KT is equal to ln PP by PN. ln PP by PN, that natural logarithm on moving to the left side, it will become e raised to. So e raised to QV0 by KT is equal to PP by PN. So we can call this equilibrium condition as equation 1. So this is the equation for contact potential under equilibrium condition. So this is the equation under equilibrium condition. Equilibrium. So now the diode is biased with some forward bias voltage or with some forward or reverse bias voltage. Here we are considering the biasing voltage as V. The V can be positive or negative. So if it is positive, then it is forward bias. Then if it is negative, then it is reverse bias. So with bias, we have to write an equation for the contact potential and the carrier concentration. So if we consider the PN junction, so this is the PN junction. So this point is xn, this point is minus xp. So under equilibrium, this is xn naught or xp naught. So these are the points, and this is x. So we know that when some external bias is applied, so with the bias, so some bias voltage, so with some bias voltage V is applied to this diode, we can see that the holes will diffuse from P region to N region. Similarly, the electrons will diffuse from N region to P region. Since the barrier width or the depletion region width is decreasing, so the holes will move from P region to N region. And we know that as the forward bias voltage increases, we can see the depletion region width is decreasing. If we apply reverse bias voltage, we can see that the depletion region width will increase, or we can say the position of xn and minus xp will change. With the applied bias, the value of minus xp and xn will change. It will move either right or left depending upon the biasing, which means the depletion region width is increasing or decreasing depending upon the bias condition. So with the bias condition, the concentration is also changing. So this equation 1 under bias condition, we can write it as PP means this is a majority carrier and PN means it is a minority carrier. So PP of minus XP naught. So PP of minus XP means the majority carrier concentration on the P side with the bias condition divided by PXN. PN of XN. PN of XN means it is the electron concentration or minority concentration, or sorry, not electron concentration, the whole concentration on the N side with the bias condition. So PP of minus XP. So under equilibrium, so we can write two conditions. Under equilibrium condition, this is PP and the holes are diffusing to the N side, and it will be PN. We are considering only the whole case. So under this is the equilibrium condition. So this is the equilibrium condition. So this is the equilibrium condition. So this is PP and this is PN. Under bias condition, the value is represented by PP of XP. This is represented by PP of XP this is represented by PP of XP, and this is PN of XN. So as the bias voltage increases, more number of holes will diffuse to the N side. This is the equilibrium case and this is the biased condition. Only we are considering the hole case. Similarly, electrons are diffusing from N to P, that we are not considered here. Hole diffusion is also all diffusion only we are considering, that is from P side to N side. So PP, PN means it is the equilibrium values, and PP of XP and PN of XN means biased values. So this ratio is equal to PP of minus XP by PN of XN equal to e raised to Q V naught minus V by KT. Equation 1, from equation 1, V0 is the equilibrium value. V0 minus V means the contact potential will change to V0 minus V during forward bias condition, and during reverse bias condition the value of V0 will change from V0 plus V. That we have already discussed in the band diagram of forward bias condition and reverse bias condition. So with the biasing, here we are assuming it as forward bias. So under forward bias condition, the hole concentration value PP of minus XP by Pn of Xn is equal to e raised to Q V naught minus V by KT. Since the V naught value is changing from V naught minus V, where V is the applied forward bias voltage. So this is equation 2. So we have to clearly understand equation 1 and equation 2. Equation 1 means it is the hole diffusion under equilibrium condition in terms of the contact potential, and equation 2 means the same hole diffusion with the bias condition. The change is the value of V0 is changing from V0 minus V. At equilibrium the value is V0, under forward bias condition the value is V0 minus V. So we are assuming this derivation in low level injection. So for low level and high level injection we have already studied. For low level injection, we can say the relative change in majority carrier concentration. That is, majority carrier concentration means at equilibrium the majority carrier concentration is represented by PP. So this is the majority carrier concentration under equilibrium. Here with the bias the majority carrier concentration is PP of minus XP0. We are assuming this as low level injection, and the majority carrier concentration, majority carrier values are assumed to be same under equilibrium condition and bias condition. There is not much change in the majority carrier concentration, or we can say the value of PP approximately equal to PP of minus XP. So this, the numerator values on the left side are assumed to be same for low level injection. And if we divide equation 1 with 2 with the assumption PP is equal to PP of minus XP, and on dividing 1 with 2 we can say PP by PN into, dividing means into PN of XN by PP of minus XP, and this is equal to right side e raised to Q V naught by KT divided by e raised to Q V naught minus V by KT. On dividing, that is e raised to Q V naught by KT by e raised to Q V naught minus V by KT. So this is 1 by 2. Since PP, the majority carrier concentration under equilibrium value and bias value are same, we can cancel that terms and we can write Pn of Xn by Pn equal to, then e raised to x by e raised to y means e raised to x minus y. So on subtracting this value, e raised to q into v naught minus v naught plus v. So minus v naught minus minus plus minus minus will become plus V, the whole divided by KT, and this value will become e raised to, right side will become e raised to QV by KT, that is Pn of Xn divided by Pn is equal to e raised to QV by KT, or we can write Pn of Xn is equal to Pn into e raised to QV by KT. So this is one equation, we can call it as equation 3. If we look at the equation 3, what is Pn of Xn? Pn of Xn means the whole concentration on N side, with the biasing. So when we apply a forward bias, the holes are diffusing to the N side. So the whole concentration on the N side is represented as Pn of Xn. So this is the biased value of holes on the N side. So all these are minority carriers. Actually this is a minority carrier equation, because we have assumed the majority carriers to be same under low level injection. So this is Pn of Xn. Pn of Xn means the biased value of holes or the biased value of minority carriers. Pn is the minority carrier under equilibrium condition. So under equilibrium, Pn means under equilibrium value, and Pn of Xn means it is the minority carrier under bias condition. So actually this equation represents minority carrier injection, or from this equation we can say that the value of Pn of Xn is a much increased value comparing to the equilibrium value. The Pn of Xn value is increased to a value that is e raised to QV by KT. E raised to QV by KT means it is the V is the applied voltage. So with the applied voltage, the value of minority carrier is increased. So this equation we can call it as minority carrier injection. So this equation 3 is known as minority carrier injection. So next, so we have obtained, so again we have to draw the figure. This is Xn, this is minus Xp. So we have the value of Pn of Xn. Pn of Xn means the increased value under bias condition. So it is Pn times e raised to QV by KT. So with the bias voltage, the minority carrier concentration will increase, or this expression represents the minority carrier injection. So this is equation 3, and now we will calculate the excess hole concentration at the edge of Xn. Excess hole concentration at the edge of the depletion region, that is Xn. So here the holes are diffusing. Under equilibrium the value is Pp and Pn, and with the bias the value is changing from Pp of Xp, and this is Pn of Xn. So with the bias voltage, the minority carrier concentration on the N side or this side increased. So we have to find the excess hole concentration at the edge of this point, at the edge of depletion region on the N side. So that value, the excess hole concentration, from the equation 3 we have understood that the excess hole concentration, the minority carrier concentration, has increased from Pn to Pn of Xn. So that excess hole concentration we have to find out. That value is represented by delta Pn. Delta Pn is equal to Pn of Xn minus Pn. the bias value minus the equilibrium value, we will get the excess hole concentration at the edge of n side. So this is equal to Pn into e raised to Qv by Kt minus Pn, and this is equal to Pn into e raised to Qv by Kt minus 1. So we have obtained the excess hole concentration. So this is the excess hole concentration at the edge. So this value is represented by delta Pn. So we have found out the excess hole concentration. So this is the excess hole concentration, that is the value delta Pn. So we have already studied the steady state diffusion equation. Before that, this is the case for holes. So similarly we can write the expression for electrons also. So this is the excess hole concentration due to holes. So equation 4. Similarly, the excess hole concentration. Similarly, electrons are diffusing from N to P. So Nn is the equilibrium value on n side, majority value on n side. Np is the equilibrium value on P side, Np, minority carrier. Similarly, with the bias, the value, more number of electrons will diffuse from N to P, then that value is equal to represented by Nn of Xn, and the value here will be Pn of Xp. Sorry, Np of Xp, electron concentration on P side. So we can write similar equation for electrons also, that is the excess hole concentration on the edge of P side. So this is delta Np. So similar equation delta Np can be written as delta Np is equal to Np into e raised to Qv by Kt minus 1. So this is equation 5. As the hole diffuse into the N region, so as the hole diffuse into the N region, they combine with the electrons on the N side, and we have already studied this the resulting excess hole concentration as the solution of diffusion equation. So these holes moving to the N side, we have found out the excess hole concentration on the N side, and these holes will undergo a steady state diffusion, and we have obtained the diffusion solution of this diffusion value, that is del P of Xn, that we have already studied the steady state diffusion equation solution, and here also we will consider that value, that is del P of Xn. So we have found out the value of delta Pn. That delta Pn will undergo a diffusion, and that solution of steady state diffusion equation value del P of Xn, the resulting hole concentration value can be evaluated, that is del P of Xn is equal to delta Pn e raised to minus Xn by Lp. This equation already we have studied. So this region is Xn and this region is Xp. So delta Pn e raised to Xn by Lp. Since holes are diffusing, we have to consider the diffusion length of holes. That is why Lp. Lp is the diffusion length of holes. We are writing the diffusion equation for the hole condition. So del P of Xn is equal to delta Pn e raised to minus Xn by Lp. Similarly, we can write the electron del N of Xp. So here electrons are diffusing like this. So del N of Xp, that value will be equal to delta Np, that is excess value at the edge of P side. So delta Np, electron excess value at P side, delta Np e raised to minus Xp So it is diffusing in the xp direction. This is the xp direction. So minus xp ln. Electrons are diffused, so we have to consider the diffusion length of electrons, that is ln. So these are the solution of diffusion equations for electrons and holes. So we know the value of delta Pn. So from 3 we can substitute del P of Xn. Del P of Xn, on substituting equation 3 on del P of Xn, that is Pn into e raised to Qv by Kt into e raised to minus Xn by Lp. So this equation can be write like this. Similarly, we can write the value of del n of xp. So these are the solution for diffusion equations. Now we have the value of del P of Xn, so we can find out the value for diffusion current. So the diffusion current due to holes. So the diffusion current due to holes, we can find out diffusion current due to holes, that is IP of Xn, since holes are diffusing in the n side. So IP of Xn is equal to minus Q into A into dP into d by dxn, d by dxn of del P of Xn. So this is the condition. The holes are diffusing from delta Pn. So this is the diffusion value. So we obtained the resultant hole concentration del P of Xn. So now if we know the value of del P of Xn, we can find out the value for current due to holes on the n side. So this is the Xn side. So IP of Xn, the current due to the diffusion of holes on the n side. So IP of Xn, that is, we have written IP of Xn is equal to minus Q into A into dP into d by dxn of del P of Xn. So on substituting the value of del P of Xn, that is minus Q into A into dP, derivative of del P of Xn. Derivative of del P of Xn we have to find out. So what is the value of del P of Xn? So this is the equation for del P of Xn. So taking the derivative of this equation, d del P of Xn by dxn, taking the derivative, this value will become delta Pn e raised to minus Xn by Lp into inner derivative, that is minus 1 by Lp. So that is the value for derivative of del P of Xn. So we can substitute that value, that is minus 1 by Lp into delta Pn e raised to minus Xn by Lp, or we can write minus minus will become this minus and this minus plus, that is Q into A into dP by Lp into delta Pn e raised to minus Xn by Lp. Similarly, we can write the whole electron current on the P side, that is In of xp, which is equal to Q into A into dn into, here there is no minus, so d by dxn, d by dxp of del n of xp. So taking the derivative of del n of xp, so here we have written the value of del n of xp, del n xp is equal to delta n e raised to minus xp by ln. So taking that derivative, we can write the expression for in of xp, that is, it will become minus q into a into dn by ln into delta np e raised to minus xp by ln. So these are the two equations. Then, so with the bias, the holes are diffusing to the n side and electrons are diffusing to the p side. We can write the total hole diffused or the total hole current measured at the edge of xn is equal to 0. The edge of xn is equal to, at the edge of depletion region, we can measure the total hole current, that is ip of xn is equal to 0. So substituting xn is equal to 0 in this equation, we can write it as q into a into dp by lp into delta pn e raised to minus xn value is 0, so that value will become delta pn. Similarly, the total electron current, so the total electron current in of xp is equal to 0. Again, we are measuring the total current at the edge of depletion region or at the edge of the p side. Xp is equal to 0, and that value will become minus q into a into, put xp is equal to 0 here, so minus q into a into dn by ln into delta np e raised to 0. So these are the two equations. You can write it as 4 and this is equation 5. From 4 and 5 we can find out the total current equation. So here if you look at the second equation, equation 5, that is in of xp is equal to 0. Here we are having a minus direction, and since xp is marked in the minus x direction, we have to evaluate the total current in the positive x direction. For evaluating the current in positive x direction, we have to consider one more minus here, so the net value will become plus. So the total current will be ip of xn is equal to 0 minus in of xp is equal to 0. Since the direction of xp is in the opposite direction, we are measuring the current in the positive x direction, we have to consider a minus with this term. So the net current value, the total current, the total diode current I is equal to ip of xn is equal to 0 plus minus. So